So, okay. So we left off kind of here-ish. Does that look right? This slide? Okay, good. After this first break, I got constellation of the week to give you, so we'll kind of start doing that sort of thing. But one of the things we need to talk about is was quite nice. Okay, this is a celestial sphere. Okay, and a celestial sphere is a scientific model. Scientific models are kind of strange because, especially this one, because it's not the way it really is. Okay, the way the celestial sphere works, this one's a little broken. I bet it's maybe 30, 40 years old. Okay, poor thing. But the way it works is those dots are stars. Okay, the bigger the dot, the brighter the star. And if you look closely, you can kind of see names, like there's Gemini. Okay, you can kind of see names of constellations on there. And this ribbon right here is the Milky Way. Okay, so that's actually the disk of our galaxy. Okay. The other thing about the celestial sphere is it's got this little, see that? That is the sun, and can you see, I feel like a magician, can you see this as July? Okay, so actually, the sun moves against the background stars throughout the course of a year. So here's September, there's the sun, okay, against these background stars. Okay, and here this is October against these background stars. So this is the celestial sphere. It's a model because the celestial sphere kind of suggests that all the stars are the same distance from the Earth. I know that's right. The celestial sphere also suggests that the Earth is at the center of everything. Okay, and the stars orbit the Earth. That's not it. Okay. Long time ago, this, by the way, would be called the geocentric, like Earth-centered model of the universe. And you kind of think, you know, how the sun rises in the east, sets in the west. It kind of looks like the sun is orbiting the Earth, but it's not. It's because the Earth is spinning on its axis that the sun appears to rise in the east and set in the west. Okay, but this is a model. It's called the celestial sphere. Oh, let's think celestial sphere. Okay, it works pretty good. So there are a few features of the celestial sphere, and they coincide with some features of the Earth. Okay, so for instance, the way this works is we'll kind of pop the Earth back in the middle there. Okay, the way this works is the Earth has a north axis of rotation right there. Okay, and it hits its North Pole extended outward. Earth's North Pole hits the celestial North Pole. So this is the celestial North Pole. That, by the way, there was Polaris there before it tore up. The star Polaris. I know, I think. Okay. This down here is the celestial South Pole. And then there's a celestial equator, which that little Earth in the middle there kind of has a ridge where the equator is. If you take that Earth's equator and extend it out, actually it would hit right about here. Which to me, it looks like if I drop it accidentally, even lightly, that's going to break right there. It's the next place. I probably should order a new one of these. Okay, this is the celestial sphere. It's kind of helpful. It's a model though, because it's not the real deal, but certain things definitely can be explained by thinking of it in terms like this. So the celestial sphere. One of the things I want to point out on this figure, this first figure, is you see here is the celestial equator. Okay, it is basically where Earth's equator extends out. Okay, this tilted line right here, remember when I walked it around, I showed you the sun was kind of in different places? That's actually the path where the sun will be. That's the ecliptic. It coincides with actually switching gears from the celestial model to the real deal. The ecliptic is, if I put, let's see, make this the sun. Okay. If that's the sun and I am the earth, I make sure I go counterclockwise, okay? Okay, so the earth orbits the sun like this. Okay, the ecliptic actually is this plane right here. And all the planets in our solar system orbit the sun in the ecliptic. Okay? So the ecliptic can be painted against the background stars of the celestial sphere as well. Now it's tilted, the ecliptic is tilted 23.5 degrees. And it kind of hurts my brain to think about that. The reason it actually is tilted 23.5 degrees has to do with the fact that the Earth's axis of rotation, which we're going to talk about momentarily, axis of rotation is tilted 23.5 degrees as we orbit the sun. Okay? So 23.5 degrees from what? Well, if you were to take a perpendicular line here, which actually probably a long time ago, Earth's axis was not tilted. We think it got hit by something about the size of Mars early on, and bada boom, it's been tilted ever since. The planet Venus, let's see, the planet, one planet inside, right? The planet Venus got hit so hard, it went bada boom. So the planet Venus actually is upside down. So it's tilted 23.5 degrees, and actually that's why the ecliptic and the celestial equator are inclined like that. So this is another celestial sphere, just to kind of emphasize something else. So I mentioned, a drawback of this, a little kid could look at this, I like just touching it. Oh, those are stars, those are wonderful stars. I love the names, make those wonderful patterns, they're beautiful in the nighttime sky, have different colors. But we know they're at different distances from us, and that's kind of emphasized with some of the stars in Perseus. All right. So the Milky Way. The Milky Way on the celestial sphere is kind of, I don't know if you guys can kind of see these lanes. Kind of goes like kind of goes down and then back up around the celestial sphere. I'd pass it around, but somebody might break it, and then I will be even sadder. Dude, really? Oh my gosh! You can see here, OLARIS, Polaris. The stick. You're like, oh. Okay. So the Milky Way is, you might think, well, the Milky Way galaxy. In fact, when we look at the Milky Way, it got its name, Milky Way, actually from looking like spilt milk. Okay, from horizon to horizon. Now, throughout the year, as we change our position about the sun, the Milky Way will kind of move and kind of have different positions in the sky. We see different stars in the nighttime sky as we orbit the sun. Okay? But we are looking into the plane of our galaxy, and that's what this looks like. So I talked about the ecliptic right here, right? The sun, right? The Earth. This is the ecliptic, or the plane of the ecliptic. Well, our whole galaxy, the Milky Way galaxy with 100 billion stars, kind of having these spiral arms that have bunches of stars and spiral arms. It's also a frisbee. There's a plane of the galaxy. Okay? And so what happens is, if we look at the Milky Way, we are looking into the plane. If we could be on the other side of the Earth, we'd see the other part down there. Okay? That's how that works. The Milky Way. And it's tipped 23.5 degrees. No, it's not tipped 23.5 degrees. I take that one back. But it is tipped from our equator. So one of the things that we're going to find out in the next chapter is kind of the history of astronomy. How did we go from, thinking that the Earth was the center of everything and the sun orbits the Earth? The sun orbits the Earth? Really? How did we change our thinking? And Galileo was kind of a piece of that. Kind of near the end, Galileo jumped in, and through personal persecution and that sort of thing, he tried to keep the scientific integrity in place. The church was kind of on him for saying the whole. He was accused of heresy for what he did by taking the Earth from the center and putting the sun in the center instead. Heaven forbid we're not the center of it all. So anyway, so that's Galileo. But Galileo actually looked at the Milky Way. This is my point. He looked at the Milky Way. He didn't invent a telescope, but he used the telescope to look at celestial objects like the Milky Way. And instead of it being just like, oh, gassy dust up there in the heavens, which they didn't really know what the heavens were made of in the 1600s, he could actually see little tiny little stars. Okay? And he's like, oh my gosh, there's more out there than we think. Okay? We'll talk about how that's significant. So on a given night, if you look at the Milky Way, you might see these kind of dark lanes. Okay, so this is the Milky Way. These dark lanes are actually, we've talked about this term before, nebula. They're just dark nebula. Okay? They're just dust that's basically obscuring what's behind it. Probably nice, bright, shining stars. All right. So this is kind of a cool concept. Everybody, what's certain in life is what, death and taxes or something like that. Another thing that's certain in life is that as you walk out this door, you have your own personal local sky. Okay, I think that's kind of reassuring. So the local sky is basically, you look to your horizon, and our local sky is kind of cluttered with trees and such and buildings. But you look towards your horizon, you go all the way around, okay? And then that dome over your head, that's your local sky, yours. Okay? I also think it's amazing, like this is your own space and time. This is my space and my time. Two people cannot be here at the same time. Anyway. So your own local sky. There are sometimes it's helpful, like this young lady or whatever she is, sometimes it's helpful to point to something in your local sky so that everybody can know what you're pointing to. And so in this example, what she's pointing to is the sun. It's kind of hard to see, so I'll kind of circle it here. Okay, here's what she's pointing to, this sun up here. And she needs to give the altitude. Now, this one you might want to listen up to these next couple of slides, especially zone in and out if you're like me during a lecture, right? But one of the things for your lab reports after you do something in this class, sometimes I ask for the altitude of the object you were looking at. Okay, and what I mean by that, and the next slide will kind of help with this, is basically the altitude is you put one hand out at the horizon and you put the other hand, in this case, up at the sun, okay, and whatever that angle is, that is the altitude of the object. Here in a minute, I'm going to show you how you can use your hand to kind of gauge altitude of objects. Okay, so in this case, she's looking at the sun. That is 60 degrees above the horizon. That's the altitude of the sun. Then the other thing is she kind of has to say the location with regard to kind of the circle. And she's identifying it as southeast. There are different ways of kind of saying the direction. So it's southeast, 60 degrees altitude. Okay? So there's a few other things with this slide. One of the things to know is right above your head is your zenith. It's your own personal, private, local sky, zenith. Okay? The meridian line, or line of the meridian, let's see, that's north, right? Let's see. That's north and that's south. The meridian is you go due north. Doesn't matter if you go from north to south or south to north, but north through your zenith back to due south. That's your meridian line. So it kind of orients yourself with regard to your local sky. All right, so here's how you would judge, like she did, like 60 degrees is the sun in that case. What you do is there's 3 angles up here, and so like I'll even put the word LAB. Okay. So one thing is you can hold out, let's see, make sure I get this right. So he's holding out his fist, okay, and if you kind of go this way with your fist, that's 10 degrees. Okay, so you could go like this. Hers for the sun, it must have been 60, so you go 10, 20, 30, 40, 50, 60. You'll make people wonder what you're doing, right? Okay, that would be how you get altitude. 20, that would have been even easier. 20, 40, 60. And actually when I'm out at the observatory, I know I talk about that a lot, but there'll actually be other friends describing things in the sky, and they'll be extending their hands. Oh, that's about 10 degrees. Like, oh, yeah. Okay. The other one is your finger is 0.5 degrees. Okay. But again, you have to kind of extend your hand, and that's kind of what that looks like. So, for instance, and now this is kind of a cool thing. I bet if I asked you guys about the moon, you'd say when its moon is rising, it looks humongous. I know that moon is bigger. I know it's this big. Okay? But next time the moon is rising like that, put out your finger and see if you can cover it up. It takes about 1/2 of your finger. Your whole finger is 1 degree. Your half a finger is a 1/2 degree. And that's about the angular size of the moon. Looks like this. Try it. Okay? The reason it looks really big on the horizon, how do I say, it's a trick on our minds. We are used to things above being close and things that are on the horizon probably being off in the distance. The thing with the moon is it's basically the same distance from us, whether it's out there or up here. It is the same distance. So our minds compensate for that, and they're like, well, if it looks like the same distance, then it really must be, I don't know. Our minds just play a trick on us. Okay? And that's kind of what it has to do with. So try that, 1/2 degree. The other thing, so that would we say the moon subtends a 1/2 degree, like from one side of the moon to the other side of the moon. Another helpful thing maybe would be we could say that the distance between a pair of stars, like for instance, these are the pointer stars, test question. Okay, these are the bowl stars in, the two farthest bowl stars in the asterism, the Big Dipper, are called pointer stars because they help you point to Polaris. But my point here is, let's see, what did we say? This was 10 degrees, right? Okay, so half of this would be the distance between these two. Okay? So would that be helpful? I don't know, it might be. We actually tonight need to talk a little bit about the constellation of the Southern Cross in the southern hemisphere. Okay? And from tip to tail, it's about 6 degrees. So the Southern Cross is a lot smaller than the Northern Cross. The Northern Cross for us is also what we call Cygnus the Swan. Okay? All right. So I wouldn't worry too much about this, but you know when I kind of turned around like this, you know, for your local sky, I did a 360 degrees turn, okay? So there are 360 degrees in a circle. Did you know that you can break degrees up into minutes? So 1 degree is equal to 60 minutes, and 1 minute is equal to 60 seconds. So it kind of looks like this. Okay, so sometimes, have you ever heard the term gnat's eyebrow? Sometimes the gnat's eyebrow, like gnat is really small, the eyebrow is really small. So anyway, if you want to get down to the tiny, tiny nitty gritty, these would be tiny angular measurements. All right, so here's something, and I almost grabbed my globe while I was over there, but I interrupted their class. One of the things you're probably already familiar with is you can take a globe, okay, and if you want to tell somebody your position, you say I am at X latitude and X longitude. It's like a grid system on the Earth. So, in fact, I looked up, you can look up everything on the internet. I looked up I kind of have it posted because sometimes it's handy. If you ever do like that software, like a star map or something like that, sometimes they need to know your longitude and latitude in order to know, to tell you what your local sky, stars in your local sky are going to look like. But anyway, lines of latitude, just like this said, lines of latitude go around, okay? Lines of latitude go around the globe, okay? And they are relative to the equator. We're about 40 degrees northish or so of line of latitude north of the equator. And notice that it goes up to the poles, that's 90 degrees latitude, right? Now lines of longitude go from pole to pole. Their longitude, kind of around, okay? I think it is so cool. So they start at 0 degrees at the prime meridian, goes through Greenwich, England, and it goes west and goes east, and it meets on the other side. This is so cool, called the International Date Line. I just think that is so cool. The International Date Line, you know how that works? Is if you go on one side, it's one day. If you go on the other side, it's another day. Other day, other day. You could just do that all day. Yeah, because it has to do with time zones and, yeah, it's just amazing. So the International Date Line. So we actually are west of the prime meridian. We're like 90 west, something like that. 94 west maybe, with regard to our longitude. So latitude from the equator, longitude, kind of lines of longitude going around this way. All right, so actually, this, and I think I've mentioned this before, the stars, if you watch them, like if you're out camping or something like that, enjoying an evening, the stars will actually relocate, stay in the same constellation pattern, but they will move throughout the course of the night. That's east, and this is west, okay? Think of it this way. It's true. Stars will appear to rise in the east, and stars will appear to set in the west. Next time you're out, kind of look at them. Stars rise in the east. What else rises in the east and sets in the west? The sun, right? Okay. So this motion of stars is the same reason as the motion of the sun. It's because the earth is rotating. Okay. So here's the deal. If you go rise in the east and set in the west, but if you go closer to Polaris, now I'm pointing up to something imaginary. I, in my own mind, have a star, the pole star is up there on that wall, about actually 45 degrees, or 40 degrees. That's our latitude. So Polaris, if you find Polaris, and we know how to find Polaris, test question, find Polaris by finding the Big Dipper and using those two far bowl stars and pointing up to the Polaris, okay? When you find Polaris, what you'll see is actually the stars will go counterclockwise around Polaris. Now, it takes a while, to swing around. But in 24 hours, and you're not going to see them all night long because the sun's going to come up, but in 24 hours, they will come back around to the same position-ish, okay? So they go counterclockwise, and the thing is, if you make your circles bigger and bigger, guess what you've done? You basically have come rise in the east and set in the west. Start little, you get bigger, 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 rise in the east and set in the west. Okay, so stars do that. It's because the earth is rotating. All right. So here we have the celestial sphere. You can tell because you have the little earth kind of snuggled in the middle of that little blue ball, hollow ball. Okay. This, I think I mentioned before, the photo here on the right, that is a star trail photo. I think it's the same star trail photo we looked at before, where basically you're trying to capture those stars moving by just opening the shutter of your lens and it's looking for that. The last bullet up there says that if you go to the southern hemisphere and try to find a star that the South Pole is pointing to, you're not going to find one. Here in a minute, I'm going to show you what the Aussies do is they have to find that little constellation, the Southern Cross, and then they can kind of gauge where the South Celestial Pole is, but there's no star there. But the point here is, like the slide says, the stars will be going clockwise in the southern hemisphere. If you've ever gone to an outback, I think, but what they used to do is when you step in, they would have like a map of the world, but it would be like upside down because it's all about the south and stuff. Southern hemisphere.
So would that be for like Polaris in like the center of that little rotational thing?
It would be Polaris. That's exactly the point. But I'm really not sure. I'd have to double check the caption. I'm almost wondering this would be Polaris. if it is Polaris, if it's in the northern hemisphere. I just don't know if it's a northern hemisphere star trail shot. It might be. So, we got
It looks like something from Sonora, Arizona, like those crazy rock formations.
yeah, it does. It does look like. Yep. It's pretty. I've never been out there to those, but very good. Okay. So if we go back to Polaris up there, and I kind of made a bullseye kind of around Polaris, like you were saying, the star trails are like a bullseye around Polaris. The deal is if I can get the whole bullseye, the whole star trail above the horizon, that star or that constellation or whatever is what we call a circumpolar star, a circumpolar constellation. Circumpolar, meaning that it's close enough to the pole star that it never sets. It's like a full. It's like a full bullseye. Its star trail is a full bullseye. Okay. We see here a person's local sky kind of mapped out. This person happens to be somewhere kind of where we are ish. You can see North America there anyway. So he looks up. You can see his zenith, right? He or she. This is their zenith. This is their horizon. Okay, and then this is their local sky. So, here's the deal. Let's see if I can kind of clean this up a little bit. Make sure I get this right. When they look for Polaris, because this is cool, I'm going to kind of show you here, and then I have it in so many words. I probably said it as much. But when they look for Polaris, this is where Polaris is on the celestial sphere. That's the broken star. Okay, that's where the Polaris is. Polaris makes an angle with the horizon. That angle right there, do you guys agree? That would be the altitude of Polaris. That is the altitude of Polaris. That's how much above the horizon it is. That altitude of Polaris is that person's latitude. That altitude equals that person's latitude. Remember what latitude is. That's basically kind of how far north or how far south of the equator you are. Okay, so that person's latitude. If I was going to draw it on here, let's see, let's pick green, I guess. That equals that guy's latitude. So you know, like pirates or just people, navigators, maritime people use sextants to kind of look at stars. Especially you could, if you were in the northern hemisphere, find Polaris, look at that angle, and know what latitude you're at. Just like that. Okay, so circumpolar stars are stars that never set. Circumpolar stars will vary with your latitude. Okay. Because, and I have one of my favorite little slides is just pictures coming up here in a minute of some star trails. It's one of my favorite slides. And I'll kind of try to show you what your bullseye would look like, what your set of circumpolar stars would look like at different latitudes. And I have a slide coming up to kind of show you the local sky. We're going to show somebody down in the southern hemisphere. Their local sky is just different than our local sky. They are privy to different constellations than we are. Yeah. So, like I said, this is like one of my favorite things. Okay, so what this says is it says look due west, which to us, I guess, I'd have to look that way. Okay, and in this case, the polar bear represents somebody at the poles. Somebody up at, let's just pick the North Pole. Okay, pick the North Pole. And if you're at the North Pole, your latitude is 90 degrees. Does that seem right? Latitude goes from 0 degrees at the equator, goes up to 90 degrees at the poles. 90 degrees south, 90 degrees north. So you're at a latitude of 90 degrees. Now, your latitude is equal to the angle of Polaris with the horizon. So, I'm not very good at this, but does that look like 90 degrees? That's supposed to be 90 degrees. Okay, here's the horizon. This is 90 degrees. So actually, Polaris is at your zenith. Polaris is right up there. That kind of makes sense because you're basically, if you're right with Santa Claus at the North Pole, you are sitting right on top of the axis of rotation, which lines up with the Polaris. Okay, so my point is that Polaris is in your zenith. So now go ahead and start to make, just kind of look up, everybody look up. Thank you. Now start to make counterclockwise circles. A little counterclockwise circle. Go ahead, you can draw with your finger. A little counterclockwise circle. Make sure you're going counterclockwise. And then a bigger counterclockwise circle. Okay, and then a bigger counterclockwise circle. And then a bigger counterclockwise circle, basically at their horizon. Okay? So, what you have just made at the horizon is what this bear is seeing. Makes you dizzy, doesn't it? Very good. I wish I could have videotaped that. Good job. So, before I move on, does this make sense? Remember, circumpolar stars are stars that basically, the star trail makes the whole enchilada, the whole circle. Does this make sense that all stars are circumpolar? All stars are circumpolar. Because they never set. They never rise in the east and set in the west because they're all bullseyes. Okay? Complete circles. All right, so let's change, a drastic change. I don't know if Jamaica's near zero, but Jamaica's at least warmer. So let's go to the equator. And we're going to do a kind of a similar thing. I don't know. All right, so if we're at the equator, I'm headed west. Okay, this is west, right? I'm at the equator. I'm getting north is over there. Does that seem right? Okay. So I'm at the equator, 0 degrees latitude. So if it's 0 degrees latitude, the angle of Polaris must be 0. Oh my gosh. The angle of Polaris with the horizon is 0. So let's look north. Let's go 0 degrees from the horizon, and there is Polaris. You'll be lucky if you can see it. So there's Polaris, and let's go ahead. I'm not going to make you do this, I don't think. Shit. But let's go ahead and make counterclockwise. Make sure we're going counterclockwise. Yeah, this way, right? Yeah, because that clockwise. So counterclockwise, little arcs. There's one arc. There's a bigger arc. And I can't make a full star trail because the horizon is, it's right on the horizon. There, okay? Now, when I get to my east and west, basically I make an arc like that. Okay, then I go over like this in my local sky, and actually then I'm going to kind of make little circles around the South Pole, going coincidentally clockwise. Oh, okay. So that's how that works. And that's why you get that sort of star trail there. So for us, I'll have to double check. I think we're 40 degrees-ish. Okay? Latitude, so that means that the altitude of Polaris is about 40 degrees. So we have a bullseye that's about like this. Okay, circumpolar stars. The other ones are appear to rise in the east and set in the west. Okay. So here we have a pair of local skies. Okay, so remember, local skies is your own private little dome. Anybody in here watch the show, The Dome? Where the cow splits in half? No? It's like a survivalist thing over there. So anyway, so a little dome above these people's heads. But can you see where the stars are totally different? Okay. So what these folks see will vary. Now there's too many L's, latitude and longitude. But what these folks will see will vary if they go different latitudes from the equator. Okay. But if they vary their longitude, it's okay. So it works like this. I can't see it very good. Let's see. looking to find North America in there. Yeah, okay. Okay, so there actually is a place over here in the USSR, right? That's at our same latitude. Our same latitude. And their local sky is going to be exactly the same if you're at the same latitude. Okay. But if you start to change longitudes, okay, then then it's going to be different. All right. Okay, so here are a pair of situations. We have the northern hemisphere on the left and the southern hemisphere on the right. Okay. So in the northern hemisphere, of course, we are awesome. We have a pole star, okay? And do you guys remember that Polaris actually is part of the Little Dipper? And it's kind of a neat place with the Little Dipper. It actually is the end star in the handle of the Little Dipper. It almost looks like somebody did that on purpose. It almost looks like somebody did that on purpose. Polaris is like, the Big Dipper is really obvious. The Little Dipper has a bowl and a handle. And Polaris is the end star in the handle of the Little Dipper. And what this is showing, if you kind of look at it, this is position 1. This is position 2. Kind of see it kind of ghosty there. This is position 3, and I believe they're 2 hours apart. This is position 4. Can you kind of see how the Little Dipper swings around? And coincidentally, not so surprising, the Big Dipper swings around too. Okay, it all swings around. For us at this latitude, the Big Dipper is a circumpolar constellation. Okay, they never set below the horizon. Okay. So this is kind of a standalone little couple of slides here. So we get to see different stars at in the nighttime. And to me, this makes sense. If I go back to remember, this is the sun, right? And I am the earth. I am the earth. Okay. So as it is, and of course I spin on my axis, I go counterclockwise. No, that's clockwise. I go counterclockwise. Yes, this way. That's right. Okay. So I spin on my axis. This would be daytime for me, right? And this is nighttime for me. So I see these stars over here, right? So let's see. 3 months later, I go like this. Okay. This is my daytime, and now this is my nighttime. I see different stars. It's not too bad. Okay. 3 months later, okay, daytime, nighttime. So as we orbit the sun, we see different nighttime stars. Okay. Now, if you're into like horoscope and that sort of thing, I just dabble, you know. And the next slide might make you mad because I'll show you how this works. But the way the horoscopes work is that basically, here's the sun, right? They are set up when you're born, the time, like the month that you're born in, the day that you're born, basically where the sun is passing through those constellations that you don't see at nighttime. Okay? So the sun is passing through a particular constellation. This time of year, that is the zodiac sign. And so actually that's what this slide is showing you. Okay, so if we, your authors kind of picked February and August. Okay, so for instance, the Earth is here in August. Okay, we see these nighttime stars at night. Okay, and the sun appears to be passing through Leo in August. So here's what it's more scientific than it is astrology. Astrology is not a science. So here's one. I bet you've all heard of Virgo, Libra, Scorpius, Sagittarius, but what about Ophiuchus? That's not one of the zodiac signs, okay? But it is actually what the sun appears to pass through, okay, between November and December. Okay, we're over here. See, November and December, the sun is appearing to pass through these. We're over here. November, December, the sun is appearing to pass through these. See how that works? So here we go. Oops, sorry. See, I forgot. I need to reveal that last one. Okay. So you don't have the next slide, but what this slide does is to show you if scientifically you were to come up, divvy up the year, you know, the March through March is kind of the way it is here, and where the sun is passing through, you would have to include that other constellation, Ophiuchus. It's kind of a strange little. Now, you guys all probably know your sign, so look at where your birthday is and see how many people's sign changed. Mine did too. Dude. You don't know it's yours? Oh my gosh. You need help, Kane.
No, I just really don't care about it.
Oh, okay. Very good. Well, this is a good place to take a break, and then we'll come back and do some more. 10-minute break, right? So about bottom of the hour.